Hello everyone, thank you for joining these presentations. Today I will present our research entitled Comparative Study of Pothole Detections Using Deep Learning on Smartphones. This research was conducted by myself, Ahyar Ulul Amri, under the supervision of my mentors, Mr. Gede Putra Kusuma. Our presentations will cover the following sections from the introductions, theoretical basis, methodology, result and discussions, conclusion, and lastly, reference. Okay, let's begin with the background. This research coming from the road damage phenomenon, where according to World Health Organizations, many roads in low to middle income countries have not yet met these standards. Road potholes are one of most issues, leading to vehicle damage and traffic accidents. The presence of potholes can sometimes be difficult to identify manually, especially while driving. The existence of pothole detection method become active research area where many methods are developed, starting from the sensor like accelerometer, GPS, or even LiDAR. On the other hand, computer vision's deep learning-based method become most popular method considering the accuracy and also cost efficiency offered. Pothole detections using deep learning on research-constrained widely used devices such as smartphone is relatively rare. Most studies focus on PC-based model comparisons with future mobile deployment plans. Comparative studies show that most algorithms being used are faster RCNN, YOLO version 7, and YOLO version 8. The research objective is to answer the problem statements, which are evaluate whether the YOLO version 8 based pothole detection model with transfer learning and hyperparameter tuning could perform accuracy better and also requires fewer computational resources compared to other state-of-the-art models, which are faster RCNN and YOLO version 7. The expected benefit of this study include providing new insight into pothole detection models that can be implemented on smartphones, offering a practical solutions for governments to monitor road conditions, and also providing drivers with a system that can prevent accidents by detecting potholes in near real time. The scope of this study include training and testing the model on a public dataset consisting of road images while focusing on lightweight versions of the model, which are ideal for mobile device deployment. Yeah, in the first part of theoretical basis, we cover a bit definition of object detection as a method to identify the presence of object within an image using bounding box. We also explain a bit about definition of pothole as a form of road damage, represent as a depression of the road surface with sharp angles. And lastly, we also mention about convolutional neural network as a basis algorithm for other object detection method later. There are three deep learning models for object detections being used in this research. First is faster RCNN, which is a two-step object detection method, starting from proposing the object area and also classifications. In this algorithm, we choose MobileNet version 3, which is suitable for mobile device deployment. Second algorithm is YOLO version 7 as one of step object detection model, the variation of YOLO, which have extended efficient layer aggregation network or EELAN and a scalable bag of freebies BOV. In this algorithm, we choose YOLO version 7 Tiny, which has relatively good detection accuracy. And lastly, we have YOLO version 8 algorithm, which also the variant of YOLO, one-step object detections, which have specialty convolutional model block CSP layer to convolution C2F and SPPF with anchor free. In this algorithm, we choose two variants which are small and nano, which both offer good detection accuracy and are suitable for mobile devices. The methodology begins with short explanation about the dataset. The dataset being used is a public dataset offered by 9number et al. Used to detect potholes on roads in South Africa. The images were captured using dashboard camera on the main windshield. The image resolution originally 4K in JPEG format with one class, which is the potholes. The data originally divided into two cases, which are simplex and complex, where in total there are 13,000 samples of images, but the majority had no potholes in it. Therefore, the data being selected resulting in train task data ratio 70:30. The example image from the pothole dataset shown at the right, where it mostly consists of two light conditions, which are low light and also the bright light, with variation number of potholes, negative 0 potholes, 1 potholes, or more than 1 potholes. Here are the detailed proposed solution on our research, mainly divided into two streams. The first is model development on PC, and the second one is the implementation on smartphones. The model development on PC mostly conducted using Python Google Colabs with specification of the Google Colabs using T4 RAM 32GB Intel Xenon on Linux operating system. We also use variety of library like PyTorch, TensorFlow, Keras, Ultralytics, 1B, and others. The development starting from the data input originally from 9number et al. Then we move to the data processing where each images are being cropped, normalized, and also resized. Besides, the data label also being reformatted into YOLO format and also Pascal VOC according to the model that we need to retrain later. And after that, we do data splitting, split the data into three, which are train, validations, and also tasks. And after that, each algorithm, including faster RCNN, YOLO version 7 tiny, YOLO version 8 nano, and also YOLO version 8 small, are being trained using the trained datasets, having fine-tuning 10 iterations using optimization of Bayesian search and monitored using 1B library. And after that, from this process, we're gonna have best hyperparameter tune for each models. And after that, it will be moved to next process, which is the implementation on smartphones. Firstly, each algorithm will be converted into TensorFlow Lite format, which will be suitable for Android device deployment. Both will be transformed into TF-Lite float 16 or TF-Lite integer E. And after that, we're gonna do average precision or accuracy testing into test dataset and compare the result. And after that, we will take best converted model and deploy it into an app that we have created using Android Studio. And lastly, to ensure the robustness of resource usage when being implemented on smartphone, we do simulation testing using 10 subset dataset tasks and measure the performance usage on smartphone using Android Profiler. The experimentation design and performance measurement, like being explained previously, will cover two parts, which are comparison of detection performance on PC, both for original model or also the model which have been converted into TensorFlow Lite format, where it will be evaluated using average precision or AP metrics with intersection over union IOU 0.5 and also 0.5 to 0.95. Besides, we also do comparison of smartphone resource usage using Android Studio Profiler to see how is the average inference time, the battery consumption, maximum CPU usage, and also the RAM usage over simulation of 10 subset dataset where each contain 50 images. First result and discussion will cover about the data preparations results, where it showed that the data relabeling have been conducted, where we now have YOLO and also Pascal VOC label format. We also have done data cropping, resizing, and normalization for all the images as shown in the image below. And we also have done the data splitting process to gain trend validation and test. Further, based on exploratory data analysis result, we find that most of images have 1 to 2 potholes per image, where most of potholes area are very small, it only cover less than 5% of the image area. And lastly, the pothole position are mostly centered and also will horizontally spread. The model development result on PC related to hyperparameter tuning per model using Bayesian search and monitoring with 1B shown on the left image. Further, we noticed that the YOLO version 8 small model had the highest detection performance in validations with an AP at IOU 0.5, followed by YOLO version 8 Nano, YOLO version 7, and also faster RCNN. Base model on validation set next being converted into TensorFlow Lite format, float 16 or integer 8. And we got conclusion that in general, the detection performance of YOLO version 8 small and nano models has the highest accuracy after being converted to TF Lite, float 16 and integer 8 compared to the other models. However, faster RCNN MobileNet version 3 was not converted to TF Lite considering its original model already had relatively low detection accuracy. Besides, if we see from the file size of TF Lite did not change significantly for the model except for YOLO version 8 model. The YOLO version 8 TF Lite integer 8 has 50% of the size its original versions. During the conversion process, it was decided YOLO version 7 Tiny only being converted into float 16 and faster RCNN is not being converted considering the distortions of accuracy happen. Here is sample comparison of pothole detections result from each model, seeing from variety light conditions. We can see that from bright light conditions, almost all of the model could predict the pothole accurately, except for YOLO version 7 Tiny, which missed 1 potholes. While on the other hand, in low light conditions, it's very challenging for each the models, where YOLO version 8 Small could almost detect all the potholes, while YOLO version 8 Nano could only spot 4 potholes and YOLO version 7 Tiny only got 3 potholes. Base model for each YOLO version 8 Small integer 8, YOLO version 8 Nano integer 8, and also YOLO version 7 Tiny float 16 are being implemented on Android app, as shown on the left image. Further, we also do resource usage monitoring to see the energy, CPU, and RAM usage per model using the help of Android Profiler, as shown in the right image. Here are smartphone resource usage comparison results. First, YOLO version 8 Nano has the fastest average inference time with 0.72 seconds per image, followed by YOLO version 7 Tiny 1.04 seconds and YOLO version 8 Small 1.33 seconds. Next, YOLO version 8 Nano has the lowest average battery consumption in the light category, which only used 48%, followed by YOLO version 8 Small with relatively same 48% and YOLO version 7 Tiny 54%. Third insight is YOLO version 8 Nano has the lowest maximum CPU usage, which only 35%, followed by YOLO version 8 small 39% and YOLO version 7 tiny 44%. And lastly, we found that YOLO version 8 Nano has the lowest maximum resource usage at 133 MB, followed by YOLO version 8 Small at 166 and YOLO version 7 Tiny with highest 263 MB of RAM usage. Here are the conclusions of our research. First, YOLO version 8 Nano, especially the integer 8 version, is the most effective model for pothole detection on smartphone, outperforming other models like YOLO version 7 and faster RCNN in both detection performance and also resource efficiency. Second, the research has significant implications for enhancing road safety and urban transportation system by integrating smartphone-based detection system. Our study has shown that the model of pothole detection could run efficiently on smartphones which originally have very limited resource, and also it showed it has high accuracy and also fast inference speed compared to previous work from Zhengzhou or Gachar. And lastly, the study highlights some limitations, including performance variability under different environmental conditions. Additionally, exploring advanced optimization technique and an adaptive algorithm could further improve the detection accuracy without compromising the resource efficiency. So here are some references being used in this research. Next, we also use this reference. And lastly, we also use this all reference. That's all for our presentations. Thank you so much for your attention from the beginning to this end. We very hope that our research could be beneficial for citizens, government, and also research community. Thank you very much. See you everyone.